It's about an hour. Right?
If you take even less, then the average length of the seminar might actually go below 1 hour. Integrated over the semester.
Let me introduce you to someone. Felix.
Just 1 second.
This is Mark. Oh, Felix is really long. He's a lot of your papers.
I've read a lot of, nice to meet you.
Yeah.
So you're
PhD now?
Yeah. Okay.
And helping to his papers a lot.
Sorry, I have the training about how
Monday and Tuesday and Wednesday.
So are you planning to visit the Cambridge University? Okay.
I've never actually didn't have those yet.
I don't know where.
Yeah, some bounds.
Yeah.
Well, I think we can, but filming it now.
Using
Okay.
yeah, of course.
Do you remember what I was asking David? We can just write. Well, not necessarily. Yeah, for example, but just find it.
Yeah, it's insane. See what happens. Everyone gets back.
Too likely otherwise. If it is a successful, then it's fine, and that's what we.
Maybe it's time to start. Okay, children.
Yeah, sometimes it works. Yeah.
And I have to repeat the same sermon each time. So this is a Blackboard talk if you haven't noticed it. So if you want to see anything, I recommend you come forward. If you don't want to see it, go backward. So today is Mark Wilde speaking. Mark is the author of a highly recommended book on quantum channel theory, which is published by Cambridge University Press. So you just have to go down to the bookshop and buy it. And he will be very happy if for every copy sold, I guess. So, and today he will talk about something which is not yet in the book, about strong converses for entanglement-assisted capacity. So.
Okay. Thanks for the intro. I think that was actually a comment of the referee that there needed to be something about strong converses in the book. So, it's very nice to be in Cambridge. I've actually been watching the videos all semester, wishing I could be here with everyone, so it's nice to finally be here. The topic of the talk is strong converse for entanglement-assisted capacity. I'm going to explain a bit what this means, because I'm assuming that most people in the room might not know what it means. And I should also state from the beginning that it was known before this work that a strong converse holds for the entanglement-assisted capacity via a different approach called the quantum reverse Shannon theorem. But we wanted to see a different approach. We wanted to see a different approach for proving the strong converse, and so that's what I'll talk about today, what's in this paper. So just a bit of background. What do we mean by entanglement-assisted capacity? I like drawing these pictures because it really helps, at least me, understand these different protocols. So the double lines are classical information, and by this I mean that Alice is preparing a perfectly correlated classical state on systems M and M prime, and she wants Bob to be able to recover this correlation. And before communication begins, they're allowed to share entanglement on these two systems that I'll call TA and TB. It's entanglement of an arbitrary form, so any entanglement that they wish. So maybe in some sense this setting is a bit magical, but we do this quite a bit in quantum information theory. So Alice then combines her share of the entanglement and the message that she wants to send, acts with some encoding, and then output are n systems, little n systems, that can be fed into little n instances of the channel big N. So this encoding is just some arbitrary, completely positive trace preserving map, and the channel is the same channel over and over again. So it's this IID memoryless setting. Then Bob gets the outputs of the channel, combines with his share of the entanglement, does some decoding, and then out comes a classical system that we'll call M hat. And what we'd like is for these two systems to be perfectly correlated as possible. Okay? And so what we do is we define a bit of notation here, an NR epsilon protocol to be, the rate is R, and this is just the log base 2 of the size of the message set, divided by the number of channel uses, so it's bits per channel use, and it has this parameter epsilon if the error probability is no larger than epsilon, where epsilon is just some, think of it as a small positive number, right? And we say a rate R is achievable. I mean, these are things that Shannon did many, many years ago. What he did was to coarse grain away all other parameters besides the rate, since in a communication context that's what we care about. So that a rate R is achievable if there exists a protocol in NR, then we allow for a slight deviation from the rate. If there exists such a protocol for all choices of epsilon and delta that can be arbitrarily small, and then we allow for a large number of channel uses. Okay, so that's the basic setting. And we define the entanglement-assisted capacity. So I'll just write this as EA capacity as the supremum of all achievable rates. So this is an operational definition of capacity. It's just a function of the channel alone. Okay, so you have a description of the CPTP map N, and then we have this operational notion of capacity. And from all of this, you can see it's just a function of the channel. So over a decade ago, in 2001, both Bennett and others at IBM, including, I guess it was Shore, Smolin, and Thapliol, and Halevo, I guess around the same time, proved that this capacity is equal to something that I'll call the quantum mutual information of the channel N, and it's just defined as the maximum of all input density operators to the channel of the mutual information that you could establish with the channel. So the mutual information is defined as this linear combination of entropies, von Neumann entropies, and the state omega. I'll define it in a particular way. It's actually very similar to a way that Will Matthews defined it in his paper with Stephanie Vayner. So the state omega will take, I'll define this in a second. We take the channel, have it act on this operator, gamma, and then sandwich that operator by rho a raised to the power 1/2. And this gamma is it's kind of like the maximally entangled state, but unnormalized. Okay, and then if I write m in this way, I just mean the outer product of this vector with itself. Okay, so you can also think of this as just an optimization over all bipartite pure states that you're feeding into the channel, right? So if we want a picture for this, we could say, well, you're preparing an arbitrary bipartite pure state on systems A and A prime, feed in A prime to the channel, and then you get some state omega. Compute its mutual information, and then maximize over all such mutual informations, okay? And I talked with Igor Devitak once about this, and he considers this one of the most beautiful results in quantum information theory, because and I agree with him, because what you find is the mutual information is the answer to this question of entanglement-assisted capacity, right? And it's very much analogous to Shannon's formula for the classical capacity of a classical channel. Except here we're in a fully quantum setting. And also what's particular about this formula is that, it is the capacity. Often you find in other scenarios of capacities that you need to regularize the formula and you can't even compute what the capacity is. But here we can compute it. So that's quite nice. There's actually results of Gary Bowen, which shows that in the presence of feedback from receiver to sender, this formula is robust. The same formula characterizes the capacity in that setting if you have a noiseless quantum feedback channel. And so it's very much analogous to the Shannon setting. Okay. So one observation that I want to make for the purpose of this talk is the mutual information can be written in a particular form from which is derived from the relative entropy. Okay. So if we take a minimization over all states sigma b acting on the Bob system, and we take the relative entropy between the state omega and take a product of omega A, which is the state you get when you trace over the B system, and then tensor that with sigma B, then you can actually show that the mutual information is expressed this way in terms of the relative entropy. So just to remind you, if you haven't seen it before, the relative entropy between two states, I'll call them mu and nu, is just the trace of mu log mu minus the trace of mu log nu. Okay? And in some sense, the relative entropy is kind of like the mother entropy, because many different entropies in information theory and quantum information theory you can derive from the relative entropy. Okay, and that'll be useful for us today. So if you want to prove, if you're actually interested in proving a capacity theorem, then you have to do it in two parts. The first part is known as the achievability part. And what you do is just show the existence of a capacity achieving code. Or it's really like a family of codes that you show, as you could imagine like someone picks an epsilon and then you have to find an n large enough to meet that tolerance. And if you can do it for every epsilon, then you've shown the existence. We're not actually interested in this part today. What we're more interested in is the converse part. So here, using these definitions quite strictly, what you prove here is that if the rate is strictly larger than the capacity, in this case this number here, then there cannot exist an error-free communication scheme. Okay, and so what's usually done, and what was there in the paper of Bennett et al., and I believe also in the paper of Halevo, is what's proven is something called the weak converse. This is not meant to, like insult the authors of that work, but just to distinguish between a weak converse and a strong converse. Okay, so this part 2, this is usually called the weak converse, and the typical type of bound that you use to establish it, it looks something like this. So you show that the rate of any protocol with error epsilon ends up being less than 1 over 1 minus epsilon times the capacity. Okay, and using this definition of achievability, well, in order for a rate to be achievable, it has to be achievable for all epsilon. So what you do, to establish the converse, you take the limit as epsilon goes to 0. And then you find that, well, if the rate is to be achievable, it has to be less than the capacity, which is the same statement here. Okay, so I think a conceptual plot is very helpful to understand this. In fact, when I first started learning about this at a workshop in Cambridge in January, and Andreas was talking about strong converses, Naresh Sharma was talking about strong converses, Nella Jana was talking about strong converses. And so I saw this plot, and it really, I found it very interesting. It sort of struck my curiosity, so maybe I'll do that today for you. So this is error probability on the vertical axis, and rate on the horizontal axis. So error probability is some parameter that varies between 0 and 1. Here we'll place the capacity, and in this case of the entanglement-assisted capacity, we know the exact number. So what the achievability part is, what you show is that for any rate less than capacity, there's a scheme for communication where the error probability can be made to go to 0. And you should interpret this plot in the limit as the number of channel uses is going to infinity. Okay, and then if you look at this bound and sort of rewrite it with epsilon as a function of r and c, then you'll find a curve that kind of looks like this. All right, so I'll call this the weak converse curve. Okay, and so that's all that the weak converse establishes. And then if you look at this, you might wonder, well, if I allow for a little bit more error, would it be possible to achieve a higher rate? Because this looks like a trade-off curve. And so what the strong converse does is it comes in and it says, well, no, you can't. In fact, no matter what you do, if you're operating above capacity, you will fail. So it's a very negative statement. But we like having it because it establishes capacity as a very sharp dividing line between achievability and what's not achievable. And since we have many physicists in the audience, this should remind you of something like a phase transition, where the phase transition occurs at capacity and error probability is like some macroscopic parameter. Okay, so I prepared some statements about reverse Shannon theorem and why that leads to strong converse. But as I was preparing, I realized I had many other things to talk about, so I'm just going to skip over that. But maybe if there's time at the end, we can talk about it. So the starting point will be to use what we've been calling I guess I should ask if there's any questions at this point. I mean, because now we're going to proceed. That was like the intro, and now we're going to proceed into the technical content. Okay, good. Everybody understands, or everybody's clueless? Okay, so the starting point is we're going to use this generalized divergence framework. And I've learned that this is a very powerful framework for establishing converses of various sorts. Okay, so we can attribute this to some very talented classical information theorists, Yuri Polyansky and Sergio Verdu, and this framework was quantized by Naresh Sharma and Nakib Warsi in a paper that appeared in 2012. So the idea is this, will allow for a very general function of two states, rho and sigma. This cursive D will mean, it's just a general function that obeys one very important property, and that's monotonicity. Okay. So you should think of this function as just some measure of distinguishability, and if a quantum operation, if the same quantum operation acts on rho and sigma, then your distinguishability can only decrease. Okay? So that's the main property that we need to start with. Of course, that holds for the relative entropy, the von Neumann relative entropy. It's probably the most critical property, which makes it useful. So that's the basic thing that these guys said we need to start with in order to have a useful quantity. Okay, and then it turns out that this way of writing the quantum mutual information is very useful. So the idea is just to define from this generalized divergence a generalized mutual information. It's a function of a bipartite state, and we use the same recipe. So I'll just write it down once again. Okay. And so this is the generalized mutual information of a quantum state, a bipartite state. And from this, using a very similar kind of recipe, we can define a generalized mutual information of a channel, just as the maximization over all input density operators in fact, defined in the same way. So like we have the state omega AB that's a function of the channel and the state rho A. And from that state, we can compute its generalized mutual information and then maximize overall inputs. And this is what we'll call generalized mutual information of a channel. Okay, so why is this useful, right? Why? Well, it allows us, using this monotonicity, we can relate error and rate to an information quantity, which are the main things you need to do. These are the main parameters you need to think about if you want to prove a strong converse, right? So, Okay, so actually I think I can reuse this. That's nice. So we were looking at this plot before, and this figure depicts any general scheme for entanglement-assisted classical communication. And if you're trying to establish a strong converse, you need to think about any possible scheme and bound, find some bound in terms of rate, error, and information quantity. So if we think about the success probability, right, it's actually, if I were to do a test, if I were to have access to the M system and the M hat system, and then I were to just ask, are the values in these registers equal, right? Then the probability that you get the answer yes is the success probability, okay? So, I'll just write that down. The probability that the outcome of this question, when you ask it, is yes. That's the success probability. Okay. So, I mean, that's fairly simple, but actually a very non-trivial. Well, it's an important observation that that these guys really made in establishing the best converses. Okay. Now, suppose that the channel is actually a really bad channel that we don't like, okay? What it does is it traces out what you're inputting, so it throws it away and replaces it with some other state. So this is the worst possible channel. Some people are surprised to learn that that is a channel when I say this. But like, you kind of learn when you study quantum information theory that anything is a channel, right? It can be expressed as a complete positive trace preserving map. So even that is a legitimate channel. So the channel that throws away, that ignores you and puts something else there, if you were to ask this question, are the values in M and M hat equal? Well, we're going to assume that the distribution on M is the uniform distribution, right? And then if the channel throws away what you're inputting and replaces it with something else, and you do this test, the probability distribution for the values of little m in this register are just some other distribution, right? And then if you sum over all these values, this is what's called collision probability, and that will be the probability that there's a collision between the values in M and M hat. But in this case, you can see very easily, well, it's just 1 over the number of messages. So not very good. I mean, it's the same as random guessing. Okay. So, okay. And now what we'll do, I'll give some names to these registers. We'll call them A1 prime and all the way up to AN prime. And we'll call the state at this point rho sub M A prime N. This will be some shorthand. If the N is in the superscript, then it means all these systems here. There's this other register TB. Okay? So this is the full state after the encoding happens. And then if you trace over the M register and the entanglement that Bob has, we get a state on just A prime N. And this is something that Will, in his paper with Stephanie, they call the average code density operator. So it's just the density operator you get if you average over all of the messages and if you discard this system that Bob has. Okay, so then what was a very nice insight of the paper of Will and Stephanie Vayner, I'm not going to go through the details because it's a bit complicated, but the main idea is just to use the transpose trick like crazy. So like the fact that, in a maximally entangled state, if you do something on Alice's side, then it's equivalent to Bob doing something, also known as the ricochet trick or the spooky trick or whatever, Okay, so doing that quite a bit, what they showed is there exists a binary test or POVM. We'll call it T for test. It acts on the A system and the B systems of Bob. So that I'll label these as well, just for clarity. So using this trick, they showed that, well, if we take a purification of the average code density operator to the A system, okay, and if we send the A prime system through the channel, through n instances of the channel, so I'll write that as, so just to be clear, this actually means the n-fold tensor product of the channels. Then when you do this test on the A and Bn systems, the probability for getting the outcome T is equal to the success probability that we wrote up before. Okay, so this test is a function of the decoder and the encoder and the entangled state. Okay, so you have to kind of believe me on this step. And furthermore, if the channel is this bad one that we talked about, where the channel just throws away the input and replaces with some other states, they also showed that the probability for getting the outcome T when performing this test on rho A tensored with sigma Bn is equal to random guessing. Okay, so and if you're super interested, it's proposition 17 and 18 of their paper. Okay, so how is this useful for us? Well, we already have quantities. We have states that look like the ones that are there in this generalized quantum mutual information. Okay, so things are looking interesting. And with this generalized divergence, right now it's this abstract quantity, but we're just going to assume that it obeys monotonicity. Okay, yeah.
Result to particular for the setting, like entanglement-assisted classical capacity?
Not entirely. So there's a discussion of unassisted capacity as well, and various other settings like. I was just focusing on this one in the paper, but yeah, there are other settings, and in fact, this idea, yeah, I mean, this particular result is particular for entanglement-assisted, but then there's a way to think about it as unassisted as well. If the measurement has a restricted form where it can only be done with local operations and classical communication, something like that. Right?
Yeah, exactly.
Okay.
Then you can get results for unassisted.
Okay. Yeah. So, okay. So now, let's think about the generalized divergence between this state and this one.
Sorry, Mark, can I ask a question?
Yeah,
It would be for the case when you're always sending classical information, right?
this is for classical information, yeah. Yeah, but I think you get results for quantum communication just by teleportation and superdense coding, going back and forth in this kind of argument. If you're allowed unlimited entanglement, and you're interested in proving a strong converse, this can be turned into a strong converse for entanglement-assisted quantum capacity. Okay, so this is the generalized divergence between the full state and the product state, and then we said that many things are a quantum channel. So this test is a quantum channel, right? And if you perform the test, you get a binary distribution. So I'll just write this in some kind of notation. I think you can figure out what I mean here. So the generalized divergence between this binary distribution that would result from performing the test on this state and the other binary distribution that's the same as when you're randomly guessing. Okay. But the thing is, this bound, it works for all sigma bn's, right? So we're trying to get the tightest upper bound possible, so we might as well take a min over all of them. Okay. Now there's still a dependence of this quantity on the particular code that we're considering, right? Because the row A and row A prime n depends on the particular code, and in fact the encoder. So we can remove that dependence by then taking a maximization over all row A. Okay. And when you do so, you recover this generalized mutual information of the channel that we defined over here. So this right here is equal to the generalized mutual information of the n-fold tensor product channel. Okay, so now we have a way to relate success probability rate, so the number of messages, we defined it before, but rate is equal to log of the message size divided by the number of channel uses. So the rate is sitting in here, and we have a way to relate success probability rate to an information quantity. Okay, and this works for any quantity that satisfies the monotonicity property. So that's the power of this generalized divergence framework. If you at this point replace the generalized divergence with the von Neumann relative entropy, you recover the weak converse. Okay, so if you want to get a stronger result, you have to work with a different divergence. Okay. So what we'll do at this point is talk about this other divergence. So this divergence already has a little bit of history. It was first on the public record in the quantum information theoretic context. There's a talk of Marco Tomichel at QCrypt 2012. And then Serge Fair talked about it in Cambridge in January. And somehow Andreas and Dong and I forgot about that. And we defined it in a different context. And so this is a divergence that I like to call sandwich relative entropy, sandwich-Renyi relative entropy. So it's defined in this way. So this looks maybe slightly bizarre, but the sandwiching is, I guess, clear. We take rho and sandwich it by sigma. Yeah.
You said that if you plug in the relative entropy, then you get the weak converse. Is that easy to see?
No, it's not totally easy to see. But okay, so if you plug in the von Neumann relative entropy, you get the mutual information here,
Yes.
but then here you would get like a binary entropy,
Yes.
and if you work with that for a bit, you get the weak converse statement.
Because you need the atomic multiplicativity result only.
Yes, you need a additivity result. Yeah, it's good to attribute it to Adami and Surf. They did it first.
And then you. Okay, and that implies that.
So finite inequality, I guess.
Yeah, I'm not going to go through it carefully, but you'll get something like this, where this is the capacity formula. You have to take the limit as n goes to infinity to arrive at this. Okay. So, Marco and co-authors call it quantum Renyi divergence, and should call it whatever you'd like to call it. So for this work, we consider the regime. The only regime that's really relevant for us is when alpha is between 1 and 2, and in fact, we only really need it when alpha is in a neighborhood of 1. Okay. So there are 3 relevant properties we need for this. The first is of course monotonicity. So this was proved in Marco's paper, and we had a very similar proof in the paper with Dong and Andreas. And then the powerhouse mathematician, Lieb came in and and with Frank showed that monotonicity holds for all alpha between 1/2 and infinity. So that was pretty impressive. And but for our purposes, again, we only need it for alpha between 1 and 2. Salman-Beji, in a different paper, showed the monotonicity for alpha going between 1 and infinity. The other very relevant thing is that if you take the limit as alpha goes to 1, you recover the von Neumann relative entropy. So this is pretty important because we want to relate to the capacity formula, the von Neumann mutual information of the channel, right? So this is pretty relevant property for us. And the third, which I think is a very useful one, is that it's related to an alpha norm. Where the alpha norm of any operator is defined in this way. And we're considering when alpha is 1 or larger than 1, so it indeed is a norm. And this is a very useful property. In fact, it's the only reason that we were able to get a result, because there was some prior work with this alpha norm. Okay. So what we do then, I won't show the details, but we have this inequality here, right? We have this inequality between success probability and the rate related to information. And if you work with this for a little bit, and the sandwiched Renyi relative entropy, and from this generalized divergence framework, we can define a sandwich mutual information of a channel. It would be defined like we defined it before. I think, it's still kind of written here. So min over the sigma b's, max over the rho a's. And if you rewrite this a bit, you'll find this bound. Okay, so this is pretty relevant for us, right? Because it's an upper bound on the success probability of any entanglement-assisted communication scheme. We're in the regime where alpha is larger than 1, right? So this quantity is positive. This quantity should be related to capacity in some way, right? Because we have this property where the Renyi relative entropy is related to the von Neumann one, and from those we get the mutual information. So you can kind of already see, well, if the rate is larger, if this term is larger than this one, then, and this is always positive since we're considering alpha larger than 1, there'll be an exponential decay in the success probability. So like the idea, if rate is larger than the capacity, then with the statement, no matter what you do, you'll fail, right? So the goal now it shifts a bit. If we can prove that this function here is additive as a function of quantum channels, then we'll get the result. So the goal will be to prove additivity, meaning that for all finite n, we can show that this is a function of a single instance of the channel. Okay. So many results in quantum information theory boil down to getting additivity, and this is no exception there. So just thinking for a bit, if we prove additivity, the bound will be like this. And then what you can do from here, I won't go through this argument in detail. We're actually running out of time. Is you start by supposing that the rate is strictly larger than the capacity. In fact, maybe we should draw a little picture here just for visual. Okay. Then what you can do is tune this parameter alpha, such that this Renyi mutual information will be between the actual capacity and the rate, because we're assuming this strict inequality. Okay, so you tune it in such a way you can find such an alpha for which that holds, and then once you have that, you're really done, right? Because r will be larger than this. This is a positive number. This is a positive number. Taking the limit, there's an exponential bound on the success probability. Okay, yeah.
Maybe I missed it, but how do you get this inequality piece smaller than?
Well, I was saying, suppose we could get additivity.
No, sorry. The one up there. Yeah, this one.
This one, yeah. So that was another thing I said I would ignore. But what you do is you substitute the sandwich Renyi entropy here, right? And then you'll get the classical. Okay, so maybe we'll write it out. So you'll get, if we evaluate this sandwich Renyi entropy for classical commuting states, we'll get this kind of expression. Right? And from this general argument and the fact that the sandwich Renyi entropy obeys this monotonicity, we'll get this, right? So then what you do is you drop this term. These are all positive numbers, so you can drop them. And this will be lower bounded, this whole expression will be lower bounded by this and the log of this. And you rewrite it, and you get this one.
How do you get r in this expression? Sorry.
1 over m. 1 over m. So m equals 2 to the nr, right? Sorry, I mean, that's a good question. I really should have explained it.
In this way, you get an upper bound on the strong converse capacity. Right? So you
Yeah.
think that if R is greater than I tilde,
It comes from the direct part of the entanglement-assisted capacity.
Yeah, I mean,
go to
we're starting from this assumption, right? R is larger than capacity, so that's your
okay.
rate you're operating at. Okay. Okay. So.
I guess you also have to know that, like, for alpha strictly bigger than 1, this thing is strictly smaller than r.
You can tune alpha.
You need the convergence from part 2. The fact that the
monotonicity in
Yeah, but you sort of need to know that 2 is strict, no?
Yeah, you need a monotonicity in alpha.
But then it's also strict, that it's like strictly bigger than the other if alpha is not equal to 1.
Yeah.
no, that's not necessary.
Otherwise, in your exponent, you get a 0 maybe.
All you need to make it smaller than r. So that will be given if it's sufficiently close to the other quantity. Doesn't matter how it converges.
If
All
you're
you
on the
need
wrong
is that
side of
you
the
can
end.
choose alpha small enough that it's closer to I of n than to r. Maybe equal. That doesn't help because you're looking only the difference between r and I tilde. No?
It has to be continuous.
You need a convergence.
Yeah.
Under the soup that is IR.
You need the convergence. There's this standard argument that Ogawa and Nagaoka came up with. Well, okay, it's a bit more slight. In fact, I'm not telling the whole truth. What you can do is relate to a traditional Renyi relative entropy without the sandwiching, so the usual one that appears. And that's at least how we did it in the paper. And then there's this sort of derivative argument. Just to prove that well, you can actually make this sufficiently close to the capacity and sandwich in between capacity and R. But I'd like to get on to just the final part, like how we actually prove the additivity, and I'll keep it brief. Okay, so the useful property is this relation to an alpha norm, okay? And we can write this mutual information as a max over rows followed by a min over sigma b's and the log of this, well, I'm going to write it in a slightly different way. So let's define this gamma to be when the channel acts on A prime of this vector that looks like the maximally entangled vector without a normalization. And with some manipulations, you can rewrite this mutual information in this form. Okay. And what you can then show, if you focus on this quantity, this quantity is concave in rho the way that you show this is that you can use Holder duality and re-express this norm as an optimization with respect to the states with respect to the conjugate norm. And then you have to invoke the Lieb concavity theorem to see that particular expression is jointly concave, and from that you can get concavity in rho. Clearly I don't have time to talk about that. From the fact that this is a norm, this quantity is convex in sigma b, and so then the minimax theorem comes into play. Okay? So, okay, then I'll just quickly quote the main result of this paper by Devatak, Marius Younge, Chris King, and Riskai. Multiplicativity, that's a hard word to say, so I didn't use it in the talk. But this paper is 05, 06, 196. What they showed, the paper is called Multiplicativity of Completely Bounded P-norms implies a new additivity result. And if you look at that paper, it's a very long paper, and they have a very useful theorem which gave us our main result. And that is, if we define a completely bounded norm, a 1 to alpha norm, I'm just going to define the particular case that's useful for us. They have very general sorts of norms that they consider. And this is a completely positive map. And this is defined as a maximum over all density operators acting on the A system. Oops. Use this gamma. Okay, so this gamma M is defined in a very similar way. It's the Choi matrix for the channel. What they showed is that for any two, this was their multiplicativity result. For a tensor product of two CP maps, they show that this norm is multiplicative. Okay. So if we want to prove additivity of this sandwich mutual information, then we just use this multiplicativity result. So this we can rewrite, we can use the minimax theorem and rewrite this as a min over the sigma states acting on, it's generally entangled states on Bob 1 and Bob 2 systems, then a maximization over the rows, and we can use this, actually, let me just use this definition here. Okay, so we have this sandwiching by the sigmas. So this notation is slightly awkward. What I want to say here is you have the map, the tensor product map, and then you sandwich that by the sigmas. Okay, and that map itself is a completely positive map, right? Like if we take the density operator, the map where we take an operator x to this right here is a CP map. Okay, so it falls within this framework, right? Because this result they had was with respect to general CP maps. So then what you do is just, well, restrict the minimization to be over tensor product states, right? And actually, I'm going to define this as theta of sigma, okay? And once you do so, you can rewrite this as sigma p1 composed with n, and then tensored okay, so we're pretty much there, right? I mean, we just need to invoke this theorem, the main result of this paper, that this is multiplicative. I'm missing logs. Okay, so the norm is multiplicative. Under the log, it becomes additive, and then we're pretty much done. Okay, so I'll just finish it off. And using this and induction, there's also, if you want to show additivity, you need to show the other inequality, that this is larger than this. This was proved in a paper of Salmon-Beji on this Renyi entropy. And so then once we have this, we can use induction to conclude the desired additivity result. So we can conclude that this function is additive. And then we're done by those arguments that I gave before, but I didn't justify. Okay, I'll stop there. I'm over time.
Well, thanks very much. Any more questions?
So I might just say some things if there's no questions. Okay, sorry.
So I suppose your exponent is optimal. Looks like.
I think optimal to a
Like,
constant,
like
right?
linear.
Because it's the best you could do would be random guessing. Like if you have an exponentially small success probability, that's essentially the same as random guessing, right? Up to a constant.
I mean, the exponent is just linearly. It's just exactly the difference between how much you code and the rate, right?
No.
And the optimal rate, if I'm not mistaken.
No.
You take limit n alpha going to 1.
Yeah, but then alpha minus 1 goes to 0. There are two contributions.
It's like,
Yeah.
right, you're right.
That still could be optimal. We don't know that. Where's Milan?
Right.
Oh, they're hiding.
Yeah, go.
Just as a small comment, because it's something I noticed. I realised I had overlooked that the sort of idea of putting of relating the problem to this this testing, and then using the monotonicity.
Yeah.
That's definitely already in Hayashi's book, actually, in this
Okay.
proof. Well, in his way of proving the Ogawa and Nagaoka.
Oh, okay.
Which, in fact, this is almost like a really beautiful kind of complement to, right? Because they use the old-fashioned Renyi entropy and
Yeah.
applying it to CQ states.
Right. Yeah, I didn't realize this generalized divergence. Or I guess he was just using the Renyi divergence.
He does it in a very specific way. But
Okay.
the proof technique is
Yeah, I mean, you might be able to argue that it was already there in Ogawa and Nagaoka,
Oh,
and then it
yeah.
goes back to like Arimoto.
well, I
and
think
Seven
and then maybe even to Strassen as well. Anyway, there's a long history.
We can keep going back.
There's a long history.
Trace
yeah.
it to the-
But it is anyway. Also, just wanted to mention that there's a
Yeah.
nice complementarity to these
I
results.
should look at that. I mean, I've read parts of Hayashi's book, but not the whole thing. Do you know which chapter it's in?
Might be 9,
Okay.
8.
Yeah, so just a concluding statement, like the main motivation for looking at this, like a big pressing open question has been to look at strong converse for quantum capacity. This is something Andreas was doing and the rest was doing as well. And the idea is maybe this approach might be helpful, but it's eluded us so far. But at least like this generalized divergence framework is nice to work with. But the trick is like picking the right divergence from an infinity of possibilities, right? Yeah, and then another type of thing you might look into is I gave this plot at the beginning of this sharp, transition, but Marco can give you very refined plots in the case of communication over channels with classical inputs and quantum outputs that are more refined for finite end, and so you see a smoother transition, and so that might be something to look into for the future as well.
Yeah.
What was vaguely their additivity result?
What's that?
What was the additivity result in the Demeter-Junge?
Oh,
Vaguely-
so they defined this completely bounded norm in a very general way, but a way to relate it to our situation here, they had an observation that a special case of their norm was a norm of this form, okay, which is a function of a CP map. And then the main result of that paper was that if you evaluate this norm on a tensor product map, then it's just the multiplication of the individual channel.
But they have
channel
another.
norms.
They have another corollary when alpha goes to 1. The additivity result they mentioned in the title is to do with this.
It's a quantity called reverse coherent information, which, in my opinion, has escaped a compelling operational interpretation. And they discussed that in their paper. So that was, but the main thing was, I think they were just interested in the fact that this was multiplicative. And so the result here gives an operational relevance to the main results of that paper. Okay.
There are no more questions, and let's thank Mark first of all.